So today we will have more examples about functions, function composition, and function inverse. And we will start by question 1. As you can see in the classroom page, we have in question 1 a simple question about a function f, where f is basically defined as a function from n to n, and the set of integer to the set of integer. And the function is basically giving me the rule that the function is defined as f of n equals to 4n plus 1. Now we want to know if this function is one-to-one or not. We can verify if this function one-to-one or not by, as I said last time, you can create two different sets. Let's say this is the domain and the codomain, and we will take like sample values 1, 2, and 3. So what is the function f of 1? F of 1 is 4 multiplied by 1 plus 1. So this is 5. What is f of 2? F of 2 is 4 multiplied by 2 plus 1. So this is 9. What f of 3? F of 3 is basically 4 multiplied by 3, and this is basically 13. We can just extend the domain a little bit. Now take for example more values, like take for example minus 1. Is 4 multiplied by minus 1 minus 4 plus 1 is a 3. So it seems to be there is no similarity between negative and positive. So we can conclude that definitely every element in the domain has an image in the codomain, and this is basically a one-to-one function. So it is a one-to-one function. There is no doubt about it. The reason why I say it, because definitely every element I have in the x, you can call this x, you can call this y, and you say f of 1 is how much? Is 5. F of 2 is 9, f of 3 is 13, f of minus 1 is 3. So it seems to be there is every element in x has an image in the codomain, so the function, this function is basically one-to-one. Now let us do another example. Let us have another example. Here I will have the same function. I have a function called f, and this f is defined from the set of n to the set of n. So this is the domain, this is the codomain, and he wants me to verify that the function f of n equals 4n plus 1 is basically onto. We want to find this function is onto or not. We can do the same. We can basically draw two sets. Let's say this is x and this is y, and let me find now how much f of 1. So f of 1 is basically 5. Take 3. This is 13. Now how much 4? This is basically 17. You will find that basically every image is mapped in y, is every image in the codomain is mapped by a number from the domain. But let me try some negative value. Let me try, for example, minus 2. Minus 2 multiplied by 4 is minus 8. Plus 1 is 7. So minus 2 is 7. What about minus 3? 4 multiplied by 3 is 12. Minus 12 plus 1 is 11. So
are they still not negative values then, or minus 7?
Because you add. It's 4 multiplied by 2 is minus 8 plus 1 is
still minus 7.
Minus 8 plus 1.
Minus 8 plus 1 is minus 7, isn't it? Minus 8 plus 1?
Yeah, minus 8 plus, yeah, it's minus 7. So this is minus 7 and minus 11. And I am very confident that this function is not onto, but I'm trying to prove or disprove that. So let me try another method. Maybe I could try to do the inverse. Maybe this will be 4x plus 1, yeah?
Just before you go on, right? Where are you picking those figures for x?
Random.
Random.
Yeah, I just select the one, but I'm trying to disprove the function. I'm trying to find another image here, which basically pointing, let's say 13 has a different image in x. So I can say with confidence that this is not an onto function. So this is what I'm trying to do. Now let me try the other way. So 4x equal y minus 1, x equal to y minus 1 divided by 4. So I can conclude there is an inverse for this function. So by all means now, I can say with confidence this function is an onto. So it's true, it's an onto function. I could then disprove it when I select random values in y, in x, and map them to y, right? And I find there is a function f minus 1, an inverse for this function. So based on the definition, the mathematical definition, that a function f of x has an inverse if and only if the function is one-to-one, and we just proved in the previous slide, and it is an onto. Once I find an inverse, this is a great confidence for me. This is a great evidence for me that this function is also an onto function. Start by saying f of n equals to 4n plus 1. Okay? Now, make random values for n. Just take random values, any value that you would like to use. Let's say take f of 1. How much f of 1? 4 multiplied by 1 plus 1. So this is 5. F of 2. This is 4 multiplied by 2 plus 1. So this is 9. How much f of 3? This is 13. Now you can see that there is impossible to have one value, one n value with the same image in the domain. There is no pre-image in the domain. Now go back to the definition of one-to-one. A function is one-to-one if any value in the domain, each value in the domain has, like this is x and this is the codomain, which is y. Any value here has one mapping in the codomain in y. I cannot have the same value here. If I have one value, let's say 1, with the same image here, then this function is not one-to-one. As long in this example I managed just to do that, I managed to prove that every single value in the domain, I have 1, I have 2, I have 3, and the codomain has the one-to-one mapping and one-to-one correspondence between those values, then this function is what? This function is basically a one-to-one. Is this function an onto? Yes. I could prove that by saying, now I will take f, we just find the inverse in the previous slide. So f of y, x minus 1 divided by 4. Whether you write it f of y or f minus 1 of x. Okay, it's the same. Now take the value 5. 5 minus 1 is 4. 4 divided by 4 is basically 1. So this, now I could draw another arrow going in the opposite direction from x to y. Now take 9. 9 minus 1 is 8, divided by 4 is 8. So 9 is mapped to 2. Now 13 is mapped to 3. So I can see here from the diagram, from taking some random values, that this function is true to be one-to-one, and it is an onto function. And it is called a bijection. Question number 3. In question number 3, I have a function, and this function is basically defined as from the z to z. Okay? And this function is defined to be as f of n equals to 3n to the power 2 minus 1. Okay, so this is a 3 multiplied by n to the power 2 minus 1. Now let us take some few numbers. Take f of 1. How much f of 1, guys? It is a 3 multiplied by 1 to the power 2, then a 3 minus 1 is 2. Take f of minus 1. This is as well 2, because minus 1 to the power 2 is 1 multiplied by 3 minus 2, this even 2. Is this function a one-to-one? No. Yeah, it's minus 1 to the power 2 is 1. Multiplied by 3 minus 1 is 2. Take, for example, another one. F minus 2, or f of minus 2, and f of 2. F of minus 2 is how much? 3 multiplied by 4, 12, minus 1 is 11. Now take f of 2 again. 3 multiplied by 4 is 11. So definitely this function is not one-to-one. It is a function, but it is not one-to-one function. It is a function. I could prove and verify that this is a function. Now, very good that you ask this. Now let me show you how you can do this in Sage, okay? Now I have Sage loaded here. I will define the same function. The same function is a 3x to the power 2 minus 1, right? This is the same function. In Sage, you can define any function, guys, using this formula, similar to any Python function. Define f of x, return 3 multiplied by x to the power 2 minus 1. How much now you want to take values, like f of 2 and f of minus 2, and let us take values as f1 and f minus 1. You want to plot this function. You can use a function in Sage Math to plot the function and look how this function look like. So if you just try to plot and you pass f of x, which you just defined there, even if you are lazy to do so, you just pass the function itself here to plot it. But take, for example, the other function we just did. The other function we just did today was 4n plus 1. Now let me replace this to 4n plus 1 so I show you how a one-to-one function look like. This will be 4x plus 1. Now look, this is a one-to-one function and it is an onto function, because for simple reason here, any value in the x has different value in the y. Any value in negative x has a different value in negative y. So this is definitely a function which is one-to-one and an onto function, and it is definitely a bijection, and it is also has some inverse. And the inverse, by the way, as we calculate it, was basically we calculate the inverse to be, let me verify, it is y minus 1 divided by 4. Now let me put just that, x minus 1 divided by 4, and let me just plot it. It is the same image. So it's just like an inverse. It's like an image and its inverse in the mirror. So it's a mirror image of this function. And later on I will teach you how you can use Sage to verify whether a function has an inverse or not. Now go back to the question that we were working on. So I was working in this example, in this question, and basically what I have done is I have a function which is basically called 3 multiplied by n to the power 2 minus 1. Is this function 1 to 1? And the answer is no, because what I can see, any value in the negative with positive in the z element is basically 1, not 1 to 1. I have f of 1 2, and f of minus 1 is also 2. Now consider this example. If the domain and codomain are given to you to be the positive integers, z plus, if the domain is z plus, this function is 1 to 1, because you cannot have both elements from x with the same image in the codomain. So if you just change this z to be z plus, this function will be defined as a 1 to 1. Now in question number 4, I'm giving a function, and this function is basically f, and f here is taking the domain of real numbers, all real numbers, positive and negative, and the function is defined to be f of x equals to the floor of x divided by 2. Floor of 3.5 is equals to 3. We considered last time ceiling and the floor. Now the question is asking me to draw this function or plot it. So basically this function, if you draw it, if you have like values 2, 4, and here you will have minus 2 and minus 4. Now just let me draw them. Minus 2, minus 2, this is not minus, and 4. Now take for example 2 divided by 2 is 1, and 4 divided by 2 is 2. So the function will go from here to here. Let me choose another color so you can basically, so this is going from 1 and 2, and let me just draw 1 and 2, and let me take this. So from 1 and 2, so 2, take f of 2, f of 2 equal the floor of 2 divided by 2, which is how much? 1. So it will be here. Take f of 4, it will be 4 divided by 2, so it will be the floor of 2, which is 2. So if I could draw it, I could draw it like this, as a step. Now this should not look like a very a harsh one, because it's not a harsh step. And once you draw this, all the value for this function, you will find that this function look like this. It will behave in this behavior, where it has like a disconnection, and then it will join and make a connection. And we can verify this in Sage by just plotting. In Sage, you take the floor of x divided by 2. I already draw it here. Yeah, it's here. So in Sage, I just draw it, and you will see that the function look like steps. Like there is stairs in this function, because this is, for example, when x is really small, when x is going from 0 to 1, it's nearly moving, and when x jump to more than 2, it start to increase, and also it start to decrease as well once x reach the value of minus 2 here. Okay, now the second part of this equation is saying, is this function 1 to 1? I don't agree, because take for example, now when f minus 2 and f also 2, both they are going all the way to 1 and minus 1. They are very close to each other. When you take real values, when you take, for example, f of 0.5 and f of minus 0.5, you will see that 0.5, the floor of minus 0.5 is 1, and the floor of 0.5 is 0. So basically, minus 1, any value between 0 to 1, is very close to any value from 0 to minus 0.9999 in real numbers. So the function will never be 1 to 1 because there is a very similarity in this area here. So the function is not 1 to 1.